Okay, in this video, I'm going to show you how to conduct an independent groups, also called an independent samples t-test, by hand. And I'm going to show you a series of steps for doing that will make it pretty easy to do. So let's think about a hypothetical experiment that was introduced in a prior video. We're going to run a small pilot study just to see if there's any effect for our communication training. And basically we have participants, men and women from troubled relationships, and the independent variable is a short interactive online instruction in communication training. And some of the folks are going to receive that, and then other folks are going to receive no training at all. That's going to be our control group. The dependent variable that we're going to be measuring is to see whether after the training, individuals who participate in the training demonstrate a greater number of distress words rather than anger words when having a 5-minute discussion on a troubling topic with their partner. So that'll take place after the training. So we just want to see if the training leads to a different communication style. Okay, so let's visualize the design. Okay, and in a prior video, we showed pretty much this graphic that there's random assignment, and then there's an experimental group and a control group. So there's really two levels of the independent variable. Subjects are randomly assigned to the conditions. We have an experimental group, we have a control group, and the subjects have an equal probability of being assigned to each group. Now, typically when we talk about humans in particular, we usually refer to them as participants rather than subjects. Now, only the experimental group will complete the communication training, and then there will be a 5-minute discussion. Both members of both groups will complete this with their partner about a troubling topic, and after or as they're going through that discussion, we'll just count the number of distress words that are utilized in that subsequent discussion. Now, obviously, the research hypothesis will be that folks who were in the experimental group will learn to express themselves a little bit differently. They'll use more distress words rather than anger words, which is better for communication. So, for example, if you say, I feel upset or I feel sad, that's qualitatively better to communicate to a partner than saying, you make me angry or you make me feel terrible or things like that. So we want people to begin to sort of own their own feelings and use words that don't evoke hostility in their partner. Okay, now we can notate this experimental design to make it a little easier to understand. The graphic works absolutely, but there's a lot to it. So let's use a design notation, and we would start by saying, hey, in the experimental group, there was random assignment of participants to the group, and in the control group, there was random assignment. So we say R sub 1 and R sub 2, with the 1 referring to the experimental group and the 2 to the control group. Now, only the experimental group is going to receive the training, and we use the manipulation of the independent variable to receive a treatment of some sort, or the training in this case with an X, and then there's outcome measurement to see the effects of that. So for the experimental group, we'd refer to that as O1. For the control group, we'd refer to that as O2. So all we have to do is just read across those rows to know what happened to the experimental group and then to the control group. And in fact, because only the experimental group receives the intervention or treatment, in other words, the X, we can just drop those labels because we know right away that that's what the experimental group is. Okay, this would be referred to as a randomized, controlled, post-test only design. There's no pre-test, so we don't know entirely where these folks were on the dependent variable prior to the intervention. So it's not the best design in the world, but it'll suffice for our example here. Now let's walk through the steps. We have 10 steps to conducting a statistical test and then making a decision regarding the null hypothesis. And so we'll just walk through each of these steps. And for your convenience, on the left side of the screen, you'll see that each of the steps is numbered, and we'll progress through all of them as we go through the example. So the first question we ask is whether or not there's a testable research question. Okay, we always have to have a testable research question that can yield hypotheses or answers, right? So here's the question that we came up with, right? Something along the lines of, Does an online communication training program increase the use of distress words by the trained partner when a couple has a subsequent discussion about a troubling marital issue? Okay, we can answer that question yes or no. The second thing we need to do is define our population, right? And the answer here is that we're going to be working with our participants will be married men and women experiencing marital problems, and we'd like to generalize back to that larger population. Third step is then going to be to choose the correct statistical test. And to do that, let's whip out our amazing statistics selector. And the first question we're going to ask is, how many samples are there? Now, there could be one sample, there could be two samples, or there could be more than two samples. And if there's one sample, we do a z-test for a sample mean, or a one sample t-test. If there's more than two, we'll do analysis of variance. That's coming later in future videos. But we really have two samples, right? We have an experimental group and we have a control group. So the answer is 2. There are two samples, an experimental group and a control group. Then the next question we ask is, are those groups independent of one another? And the answer is yes, they are independent. Why? Because we randomly assigned folks to each of the conditions, right? So we have an experimental group and a control group, and there's really no relationship between individuals either within the group or between the groups. So the answer is yes, the groups are independent of one another. Participants are randomly assigned to one group or the other and have no relationship to any other participants. Well, if the answer is yes, that means we're going to run an independent groups or independent samples t-test, means the same thing. If the answer is no, then we would run what's called a correlated groups t-test, which in some textbooks is referred to as the dependent samples t-test as well, meaning the same thing. Let's go to the fourth step. We're flying right through these steps, and it's not particularly hard. We just need to be asking the right questions in the right order. So we have to select at this point a one-tailed, a directional, or a two-tailed non-directional test of significance. Our answer here is we're probably going to go with a two-tailed test of significance, and it's always good to sort of think through why we make this decision, especially if we're doing a one-tailed test. Two-tailed is really sort of the default, unless there's a real good reason to run a one-tailed test. Now, you might say in this situation, and some people might argue that, hey, you're really only looking for an increase in the number of distress words that are used, so run a one-tailed test. But that's really not the best way to ask this question, right? We're dealing with a new training program, right? It's not clear at all that individuals will learn lessons from the training program that will then generalize to subsequent discussions with their spouse. Just like you might learn something in a classroom, that doesn't necessarily mean you go out every day and just apply it simply because you learned it. So we're not clear that this is really going to generalize. So a two-tailed test kind of makes a lot of sense here. So we'll do a two-tailed test. Then what we need to do is specify the null and alternative hypotheses. And because we're running a two-tailed test, we're expecting in the population that the mu for group 1, represented by the sample of folks in the experimental condition, will equal the mu of group 2, which is represented by the sample of folks in the control condition. The alternative hypothesis is just that those means in the population are not equal. So that's our formal statement of the null and alternative hypotheses. And look at us, we're already up to step 6. We have to select alpha. So let's identify the size of the region of rejection. It's also called the critical region. So alpha equals 0.05. And really, what we're trying to decide here is how big this non-shaded area should be, right? Okay, and when we say alpha equals 0.05, what we're saying is if we add those two non-shaded areas together, the total amount of area under the curve accounts for 5% of the area, so 0.05. Now the big question for us is, given that we're going to be running a t-test, where exactly do we draw this cut point, right, for defining the critical region? Okay, what does the critical value for t have to be? And that takes us to step 7. Let's identify the critical values for rejecting the null hypothesis. So here's our sampling distribution, right? And as you know, this is the sampling distribution of the difference. Okay, and we just need to know where we're going to locate that critical value. Now, in order to do that, we need to know the sample size. That's n, and it's 14 for our study. Now, for an independent samples t-test or independent groups t-test, degrees of freedom will be n minus 2, so that becomes 12 degrees of freedom. Right? Our alpha we already set at 0.05, and we know that we're running a non-directional two-tailed test. So when we look this up in a t-distribution table, which you'll find in the back of every stats book, our critical value for t, the cut point where we start the region of rejection, the critical region, is going to be plus or minus 2.179, and feel free to look that up on your own. But trust me, that's right. And so we do that because at small degrees of freedom, we have a non-normal distribution of the sampling distribution. And to return alpha to a true level of 0.05, we need to push that critical value further out into the tails. So the gray area then represents the adjustment that we've made to expand the size of the area under the curve that will now essentially equalize the region of rejection to 0.05, because at small degrees of freedom, those tails are a little bit thicker than what we would expect from a normal distribution. And I have a video on that that you can take a look at, a prior video. Okay, so t-crit here now becomes plus or minus 2.179. And everything that's shaded represents area where if the sample mean falls in there, our t-ratio is located within the blue or the gray area, we fail to reject the null hypothesis. So now we've actually got to collect our data, run the statistical steps. Okay, and so I've taken some of the data, and again, a small pilot study, and I've entered it into a tabular format for calculating the estimated population variance and the estimated standard deviation. Now, you've seen this sort of process before, okay? So here are the raw data, number of distress words used for the experimental group in a 5-minute session, and here's the same for the control group. Now, as you recall, and I'm not going to go through all of this because you've done this before, as you recall, we then calculate the mean, we subtract the mean from the raw score, that becomes our deviation score. We square that, right? And the reason we square that is because if we added up all these deviation scores, they always sum to 0. That's a problem. We don't want to always sum to 0 because that tells us nothing about really the variability that's present within the data. So we have to square, and then we sum all of those square deviation scores, and we get sum of squares for group 1. We do the same thing for group 2, and we get sum of squares for group 2. Now from there, it's pretty simple to compute the estimated population variance. We're going to divide sum of squares by degrees of freedom. That becomes 14.81. And then we take the square root of that, and that becomes 3.85. That's the estimated population standard deviation. And we do the same thing for group 2. Now, the one thing I do want to show you here, this is a tabular way of doing it, okay, and it's pretty intuitive, but you can also use a computational sum of squares to do the same thing. And if you're going to do that, this will take us to the point where we've summed up our squared, it'll be the equivalent of summing up the squared deviation scores. And all you really need to do is get your x values, your raw scores, and then square each one. That will create the sum of x for group 1, and then the sum of the squared x's for group 1, okay? The computational formula is listed here. You just plug those numbers in. So this 1489, right, goes right here. And then the sum of all the x's, which was 99, goes right here. You're going to square that. And then you end up with 88.86. And then you do the same thing for the second group, the control group. Okay. Now, what's kind of cool about this is if I pull up that original table we were looking at in the last slide, you'll notice that the values that we get are exactly the same as what we would see doing it in the tabular format. And then from there, of course, you just calculate the estimated population variance and the estimated population standard deviation for both groups. Okay. All right, so after we do all that, now we actually have to go ahead and do the steps for running the test. And the first thing we do is we're going to compute the pooled variance estimate. Okay, and I've shown you how to do this in previous videos, so this should be familiar. Basically, we're going to take degrees of freedom for the first group and the estimated population variance for the first group, and then we're going to add that. We're going to multiply those together, and then we're going to add that to the degrees of freedom multiplied by the estimated population variance for the second group. That's our numerator. Okay, so where is degrees of freedom for the first group? It's right there. Where is the estimated population variance? It's right there. Okay, and we do the same thing for the second group, right? So those are already given to us from the work we've done. Okay, and then we just divide by degrees of freedom total. You might say, well, where do we get degrees of freedom total? I see degrees of freedom sub 1, degrees of freedom sub 2. Well, really, degrees of freedom total is just the addition of those two. So that's going to be 6 plus 6 is 12. Okay, so when we work out all the math, and I've shown you it all worked out here, we get a value of 11.31. The value is not really all that interpretable, but what it represents is the pooled variance estimate in the population. And we do that because we don't have any rational reason for selecting one variance estimate over another from the two groups. So we just pool the variance together to get an average. All right, so once we've computed the pooled variance estimate, the next step is going to be to compute the estimated standard error of the difference. And of course, it's the difference of independent means. Now, the good news is we've already done the pooled variance estimates, and that's entered here, right? So that's going to be 11.31 over 7 plus 11.31 over 7. We're going to take the square root of that, and that's going to all work out to 1.80. So what does that 1.80 mean? Well, again, this goes into the denominator of the t-ratio when we calculate it, and it's the average amount that we expect the sample means to vary from one another, right? The average amount that we expect the sample means to vary from one another, and we use it as an estimate for the population. Okay, so we're going to then, in the t-ratio, compare how much the sample means actually varied from one another to how much we expect them to vary from one another on average to see if the variation is more than we would expect. Okay, so the estimated standard error of the difference tells us the average amount we expect the means from the two group to vary from one another simply due to sampling error. Okay, now when we run the t-ratio, I like to call it t obtained, right? But a lot of textbooks will just say t. But by saying t obtained, we're specifying that this is the t that we're actually calculating. It's not the critical value of t. Okay, in the numerator, we have the difference between the sample means, and then we subtract out the difference between the population mean for the first group, or we're subtracting out the population mean from the second group from the population mean for the first group. Now, typically, the null hypothesis is going to state that the difference between those two population means is 0, right? So most of the time, we're going to just enter 0 there. Now, there are some instances when the difference we expect in the population, or we understand in the population between those means, is non-zero, okay? But we're not going to worry too much about that right now. So, but that's the way the formula is stated. We're going to subtract out differences between the population means. And when we work that out, it's going to be 14.14 minus 8.14, and then work it all down, and it becomes 3.34. So that is the t-ratio. You know, we call it t obtained as we're calculating it, but that's what we get from our data. So now you might be asking, okay, so now I've got a t-ratio of 3.34. The next step is to make a decision regarding the null hypothesis, and to refresh, we had determined earlier that the critical value was plus or minus 2.179, right? So we needed a t-ratio that was going to fall farther from the mean of 0 in this sampling distribution. And what did we get? Well, we got a t obtained of 3.34, which is clearly farther away, right? It's farther out from the critical value, which puts it in the region of rejection. Because of that, right, what we're really saying is, hey, you know, this difference that we observed between the means of the two groups was more than what we would expect from sampling error alone. In fact, it's quite a bit more. That's why it's in the region of rejection. Therefore, we're going to reject the null hypothesis. And the next thing we really need to do is compute an effect size. And I'm going to have a video coming on next that's going to show you how to do two different effect sizes, eta squared and Cohen's d. I'm going to hold off on doing that right now because that really deserves its own video. But the main point is we're rejecting the null hypothesis, and we really should compute an effect size to give a good index of the magnitude of the effect. The p-value that is computed once we reject as we run the test and when we reject the null, the p-value is really a statement of the reliability of the finding, how likely it is to occur simply due to sampling error. Doesn't really tell us the magnitude of the finding. So that effect size is important to add in. Okay, our 10th and final step is really not a statistical step. It's just more of a reminder to generalize back to the population, revise subsequent hypotheses. We're going to take our results and use them to inform future research. Now, when we get those results, though, we do need to format them into APA format. And the general form for a t-test is to note the specific test, t, the degrees of freedom, the t ratio, which is our t obtained, the p-value, and then the effect size. Now, the p-value is just the probability that our results could have been due to sampling error, could be attributed to sampling error. Now, when we're doing it by hand, it's perfectly acceptable to put something like this in, or just report it as this. T ratio, so we say t, and then in parentheses 12, because that's our degrees of freedom across the entire study. 3.34 was what we obtained on our t ratio. And then the p-value, all we'd say is it's just smaller than the region of rejection. We don't actually need to look it up in a t-distribution table or a z-table. So what we just do right there is say, okay, p is less than 0.05. Now, a statistical processing program would actually tell us the exact value for p. But we don't have that, we're doing it by hand. So we'll just say, okay, we rejected the null hypothesis, therefore p is less than 0.05. And I've skipped putting in an effect size until the next video. We'll add that in once we get that video done. So that's really what we're going to do next is we're going to learn how to compute effect sizes and then report them in APA format. And we'll actually walk through an example using JASP so you can see how the computer program does it.